Today we're going to learn about the trig form of complex numbers. So if you recall, a complex number is composed of something like this, a plus bi, and for whatever reason we typically use the letter z to indicate that it's a complex number. So complex number consists of a real and an imaginary part, okay? And if we were to try to graph this in like our traditional xy, that doesn't work, because how do we graph something that's imaginary? So we end up using the complex plane, which I have over here. It has a real axis and it has an imaginary axis. So if we were to just take some random complex number, let's just say 2 plus 3i, what we basically do is correlate this to a point, 2 comma 3. So we basically let the real number be where x is, and then we let the imaginary number be where y is. So if I was coming over here and I wanted to plot the number 2 plus 3i, I would go 2 and then up 3. So that would be this right here. So this is 2 plus 3i. So it's kind of weird. In the complex plane, we don't graph points, we graph numbers. So an actual number, not a point. For example, when they want us to plot the points u, v, and u plus v, as well as the origin point, which would be the complex number 0 plus 0i. So if we're adding complex numbers, remember we just add the real numbers and add the imaginary numbers together. So this will end up being 3 plus 2i. And then we have our origin, as I already said, is going to be 0 plus 0i. So if I plot those over here, and we'll start off with 0 plus 0i, then let's do 1 plus 3i. So 1 plus 3i is that number right there. 2 minus i is that number right there. And then when we add those together, we get 3 plus 2, which is right here, right? So that was u, that was v, this is u plus v. So after we've plotted them, it's asking us, does this make a parallelogram if we kind of connect all of these dots together? So remember, parallelogram needs opposite sides to be parallel. So if I'm looking at these sides right here, this has a slope of 1, 2, 3 over 1, and so does this part right here, 1, 2, 3 over 1. And then going this way, we have a slope of negative 1/2, and same thing here, negative 1/2. So yes, this thing does make a parallelogram. And one of the connections that we want to make to you is that if we actually treated these like vectors, so let's pretend like this was a vector 1 comma 3 for u and vector 2 comma negative 1. So then the vector u plus v would end up being 3 comma 2. And if we were to make these vectors, this would be where vector, let's make those dotted. So it's been a while since we've done vectors, but you may or may not remember that when you do vector addition, that one of the main ways we could do it was by creating this parallelogram. Because if we were to take this vector right here and line it up so that it went head to tail, it would form that point right there. So that was one of the things we learned about with vector addition, and it just so happens that complex number addition works basically the exact same way. So that's just one of the connections that we're going to be making throughout this lesson, is that complex number addition is basically the same as vector addition. It's probably not a huge deal, and we're probably not going to spend hours, getting into it, but it's just a neat little connection between everything that we've been doing this half of the year, that they're all kind of related to each other in some way. Let's say we started off with a number like x equals negative 3, and if I were to ask you what is the absolute value of x, you would just say, okay, well, what's the absolute value of negative 3? Okay, that's positive 3. So what if I asked you the same situation, but it was a complex number? So I had, some a plus bi, and I said, hey, what is the absolute value of a complex number? How would we go about doing that? Well, basically what the definition of it is essentially the distance this point is from that origin number, so 0 plus 0i. So this is equal to the distance from 0 plus 0i. And if we kind of break that down, it essentially works out to just be the square root of a squared plus b squared. So the absolute value of a complex number, which is sometimes referred to as the modulus of the complex number, is just equal to square root of a squared plus b squared. Now we've already been making some connections to vectors, so this is hopefully somewhat familiar to you as well. What we're essentially asking is if we had some vector that was equal to a comma b, the magnitude of that vector was the square root of a squared plus b squared. And this is basically the exact same thing. So being asked to find the absolute value of a complex number is the same thing as being asked to find the magnitude of a vector. They basically are functioning the same way. Example 2 asks us to find the absolute value of 3 minus 2i. So I'm just going to do a big old square root and take the a term, which is 3, and the b term, which is negative 2, and square it. So that's going to give me 9 plus 4 under the square root, so I get the square root of 13. So the absolute value of the complex number 3 minus 2i is a real number, square root of 13. And it's always going to be a real number, but just kind of neat that the absolute value of a complex number always gives us just a real number. So now we get to see why this is actually part of this polar unit that we're in, because we're essentially going to connect complex numbers into a polar type form. So remember, polar is r's and thetas, and we already showed that complex numbers are really similar to when we graph them, an x and a y. So if we can take x and y and relate them to r's and thetas, then maybe we can take the a and the b of a plus bi and relate those to a, r, and theta. So I'm just going to pick a random point way out here and just say, hey, this is a plus bi. And if I were to connect it to the origin, this is going to be the absolute value of that. But in polar, we would have referred to that as the radius. And we would have right here some angle. And then this value right here is a, and this value right here is b, which is essentially equal to x, and this is essentially equal to y. This is kind of neat, maybe. I'm hoping you see some of these connections here that we already have. If a equals x, we already know that x equals r cosine theta, which is actually the same thing as saying, hey, find the absolute value of this complex number. If we can find this theta value, then we can do that as well. B is going to equal y, which we already know is r sine theta. So using these conversions right here, if we have the complex number a plus bi, we can replace the a with r cosine theta, and we can replace the b with r sine theta. And then we would have this extra I, which we normally would throw in right here, so that just the trig function is by itself. So we have ri sine theta. And this is referred to as the trig form of a complex number because we're using theta, so we have trigonometry going on here. It's also occasionally referred to as polar form of complex numbers because we, again, have an r and a theta that we're using to define the complex number. Now, this gets super annoying to have to write this out all the time, r cosine theta plus ri sine theta. So we came up with an abbreviation for it. And we basically say r cis theta. And that's because r is always the same for both of these. It's always a cosine, it's always an I sine, and theta is always the same. So rather than needing to write out r cosine theta plus ri sine theta every single time, we just write this, r times, this part right here is pronounced like kiss. So we say r kiss theta. And what that really means is this, r cosine theta plus ri sine theta. 3a and b are asking us to find the trig form of the given complex number. So I personally think it's easiest to graph this. So remember that we can essentially treat this like it's the point 1 comma negative square root of 3. So if I graph this, that's going to be 1 down here. So I can make a little triangle off of this. I recognize this as a 30, 60, 90, so I now know that the absolute value of this is 2. Also happens to be the radius if we were dealing with polar coordinates. And then this angle right here, I recognize it as a reference angle of 60. Okay? So we know that we could write this same point right here. Okay? It's the point 1 comma negative square root of 3. it's the polar point, 2 comma 5 pi over 3 if I'm in radians. And there's lots of other ones we could do, right? There's lots of polar points that we could do. It is also the complex number, 1 minus the square root of 3i. So we have 3 different ways of representing this same point. And when they ask us to switch this from complex number to trig form of the complex number, we first find the r and theta, and then we can just write this as r kiss theta, 5 pi over 3. And just as a reminder, what this really is saying is to cosine 5 pi over 3 plus 2i sine 5 pi over 3. That's annoying to write all the time, so we don't bother. Now, if we were to evaluate 2 cosine of 5 pi over 3, 5 pi over 3 is 1/2 times 2, that's going to equal 1. If we were to do it over here, we have 2i. This is going to be a negative square root of 3 over 2, so the 2's cancel, and we're left with a 1 minus the square root of 3i. So these do work. This complex number can be written in this form, and it gives us the exact same thing. So that was just a little mini proof to show you that all of this stuff works, and I'm not just making it up. And that essentially, what I asked you to do here when I said convert this from the normal standard complex number form to the trig form, I basically asked you to switch it from rectangular form to polar form, just like we've already been learning about. So it's no different. 3b is a calculator question, but that's okay. We're going to pretend like I'm using my calculator while I'm sitting here. So I'm going to first graph this thing. It's down here in the third quadrant over -3, -4. I recognize that this is a 3, 4, 5 right triangle, so I now know that that's going to be 5. I can use my calculator to help me figure this out by doing tan inverse of this. It's going to give me theta as a reference. So I'm in radian mode because the direction said that I'm between 0 and 2 pi. So my calculator's in radians, and I got 927. And if I want to find what that actually is, I need to do pi plus that theta reference angle to find the actual angle. So when I do that, I get 4.07. So this, -3 minus 4i, can be written as 5 kiss 4.07. And I'd be done. And just to emphasize the connection here so that you understand that this is nothing new, it's just a new way of writing things, is if I had the point -3, 4 that was written in xy, all we did was convert this into polar by saying that this is 5 comma 4.07 radians, which is r theta. So all I'm asking you to do is switch from xy to r theta. Using the trig form of complex numbers is actually really powerful. There's a lot of shortcuts that we can use with it that make our lives significantly easier. So the first thing we're going to talk about here is multiplication. So if I have a complex number up here that's in trig form, so I have r1 kiss theta 1, r2 kiss theta 2 for z2. If I multiply these two things together, I'm going to end up getting basically just multiply the radiuses together and then add the angles together. And that will give me what this multiplication is. If I do division of these, so z1 over z2, I divide the radiuses and then I just subtract the angles from each other. And that's really easy to do compared to if you had two complex numbers. Let's say you had something like 1 plus 3i, and then you had like -2 minus 4i, and we were trying to multiply these, we would have to FOIL. Well, if we have these written out in trig form, all we have to do is multiply the radiuses and add the angles. Super easy to do. I'm just going to show you a quick proof of how the multiplication one works. So if I have z1 times z2, I'm going to write this out fully, but I'm going to factor the r1 out. So it's r1 times cosine theta plus I sine theta. And then I will have times, not plus, times r2 factored out from this one. Cosine, those need to be theta 1s, and these needs to be theta 2s. Sorry, there we go. So let's just first start off. I can just rearrange this multiplication. So I'm going to run out of room, honestly. So I'm going to kind of scoot this way over here. So I'm going to have r1 and r2 multiplied together, and then I'm going to very carefully FOIL this stuff out. So I'm going to have cosine theta 1 times cosine theta 2. Theta 1, cosine theta 2. Should have used a's and b's. That would have made this probably way easier. Next, we'll do this one right here. So cosine times the I sine theta. So I'm going to have a plus cosine theta sine, cosine theta 1, sine theta 2 with an I value there. I'm going to run out of room, so I'm going to write underneath. So I'm going to multiply these guys next. So I'll have plus a cosine theta 2 sine theta 1 I plus an I squared, that's interesting, sine theta 1 sine theta 2. Forgot to write the word sine there. Sine theta 2. So, how is that useful? No idea. But we do know that I squared is really -1. So I'm going to group these things and these things together because they have no i's, and I'm going to group these together because they do have an I value. So I'll have cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. And remember, I still have the R1, R2 over there. Then I'm going to just write it on the next line. I'm going to have these guys with the I, I'm going to just factor it out. So I have cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. And I'm not sure if you recognize it, but we have an identity. Cosine, cosine minus sine, sine. That's the identity for cosine of two angles added together. So I have R1, R2. This top part right here is really cosine of two angles added together. So theta 1 plus theta 2. Plus, now here we have a sine, cosine, cosine, sine. And whichever way you write that around, this is the identity for sine when we add two angles together. So this is really sine of theta 1 plus theta 2. And we have that I chilling there still. And we can just abbreviate this part right here, the cosine plus I sine, as kiss. Theta 1 plus theta 2, because the angles are identical, and then we have the R1 and the R2, and that is where it comes from. Whew, my gosh, that was rough. No, it's not going to be on a test or a quiz, you never need to remember it, but I made you watch it, so ha. Okay, example 4, we're just going to multiply these things. We want to know what is z1 times z2. So we're just going to multiply the radiuses. So I'm going to have 25 times 14 times the square root of 2. And then I just add the angles on the inside, which I think is probably the hardest part of this whole thing. All right, so let's see. Cheating and using the calculator, I got 350 square root of 2. And then let's see what's going on here. I need to rewrite these guys as something over 12 probably. So this is -3 pi over 12 plus 4 pi over 12. So that's going to be a positive pi over 12. Done. This is our answer. If we really wanted to, we could convert it into a plus bi form. We would just do 350 square root of 2 cosine of pi over 12. We would get 478.11. Then we would do 350 square root of 2 times sine pi over 12, and we would get 128.11 I. So I would leave the answer this way because that's how they gave us the complex numbers. So we always kind of match forms. If they gave us the complex number in trig form, our answer is in trig form. If they had given it to us in standard form, then our answer would be in standard form. 5 wants us to just divide, so we'll use the formula over there. If I divide z1 divided by z2, I just take the radiuses and divide them. It's important the order here, it matters, right? Z1 is what we're dividing Z2 by, so we get 2 rad 2 over 6, and then kiss, and then we have 135 minus 300. So over here we can simplify this, we get square root of 2 over 3, kiss, and then I don't know what that is, -165. Wonderful. And this is our answer as far as I'm concerned. If we wanted to, we could again rewrite it into standard form. We would just do square root of 2 over 3 cosine -165, and then square root of 2 over 3 times sine -165. And just so you see what that would be, this is approximately what that is. But again, this is standard form, and they gave it to us in trig form, so we're going to leave it in trig form as our answer. This extra practice at the end just wants us to find the multiple of z in 1 and find the division of z1 divided by z2. We want to do it using trig form and using standard form as well. So I'm going to start off doing the multiplication of this, But before I do that, I want to just convert both of these to trig form. So like I did earlier, I'm just going to graph this to recognize that this is a 45 in the fourth quadrant here. So I can rewrite this guy as square root of 2 kiss negative pi over 4. Okay, because the radius would be square root of 2 and it's a negative pi over 4. When I go to do this guy over here, I'm going to have square root of 3, 1, so I recognize this as a 30, 60, 90. This one is going to be 2 kiss and then pi over 6. So now that I have both of them in complex form as well, it's going to be a little bit easier to do that second half. So let's do the multiplication first, so z1 times z2. And we'll do it the old school way. So that's 1 minus I times the square root of 3 plus I. So I have to FOIL here. So 1 times square root of 3, 1 times that plus I times this. I get a minus square root of 3I, and then I get a minus I squared. So if I could just continue with this, this is really a minus 1, so I really have a plus 1. So I have a square root of 3 plus 1. And then over here, I can factor out an I, and I would have 1 minus the square root of 3i. So this is actually in a plus bi form. Just looks kind of gross, I think anyway. So if I wanted to use the complex form to do this, all I have to do is just multiply the radiuses. So I get 2 times the square root of 2, kiss, and then I need to just add negative pi over 4 plus pi over 6. So doing that, I'm pretty sure gives me negative pi over 12, and then I would just expand this by doing 2 times the square root of 2 cosine of negative pi over 12, and when I do that, I'll get 2.73, and then do the same thing, 2 rad 2 times sine negative pi 12, and I get a negative 0.732i. And if we were to do square root of 3 plus I, that's 2.73, and 1 minus the square root of 3 is 732i. So we get the same answer no matter which way we did it. One might be easier than the other. I don't know. You tell me. If I go to divide these now, so if I divide while they're in standard form, that's going to be 1 minus I over square root of 3 plus I. And remember, we're not allowed to leave i's in the denominator, so in order for me to do this, I need to rationalize by multiplying by the conjugate, so top and bottom by the square root of 3 minus I. That means I need to FOIL on top, so that's going to be square root of 3, then minus I, then minus a square root of 3i, and then plus I squared, all over. On the bottom, I'm going to get 3 plus 1. Yeah, 3 plus 1. So up top, if I kind of group things, I have a square root of 3 minus 1. That's coming from the things without an I. And then I can do minus 1 plus the square root of 3 times I. So I factored out a negative and the I, all over 4. So I can just do each individual one over 4. And then I would just have to type this in my calculator to see what I get. So if I type it in the calculator, I get 0.183 minus 0.683i. So that was doing it the old school way. New way just says, hey, just take the radiuses and divide them. So I'm going to have square root of 2 over 2, and then just subtract the angle. So negative pi over 4 minus pi over 6. So doing that gives me, I think, negative 5 pi over 12. And then I just, in the calculator, do square root of 2 over 2 cosine negative 5 pi over 12. That gives me 0.183. Square root of 2 over 2 times sine of negative 5 pi over 12, and that gives me negative 0.83, and then I just include the I. So either way it works. One way, there's a lot less craziness going on, I would say.